So our next speaker is Mr. Malvinder Singh Rooprai. He made the long way from India, and he's a contributor at GPD Finland since many, many years. So he's also my nice colleague and friend from Rooprai Advanced Interlayer Solutions. And Malvinder is handling our technical consultancy in Asia Pacific region. And he's also the country leader in India. And his topic today will be new design possibilities in laminated glass with an improved stiff PVB interlayer. Malvinder, welcome, and the floor is yours.
Thank you very much, Ingo, for the nice introduction. Yeah. So today I'm here to talk about new design possibilities with laminated glass with improved stiff PVB. So the word improved is very much of central to our company, and I would like to emphasize on that. So if you know about Kuraray it's a Japanese company, and the improvement is very much central because we follow the principle of Kaizen, which means always there is a room for improvement, no matter it is big or small. Yeah. Yeah. So I have an obligation to talk about our company. So we are a global company, and we have presence all over the world. And it's interesting, when I was applying for visa to come to Finland, I was not aware we have an office in Finland as well, although it's not related to our advanced interlayer solution business. It is something related to the paper industry. Yeah. Okay, so we do have some exciting polymers which find their application other than the glass industries. So we say in the morning when you wake up from the bed, you brush your teeth, and from that time when you go to bed and you sleep, so you are definitely coming in contact with polymers which are made by Kuraray. So we have very interesting polymers which find their application in dental industry, in paints industry, and of course there are some polymers which find in construction industry. We have man-made fibers for reinforced concrete. Yeah. And specifically talking about the vinyl acetate company, so the interlayer the interlayer business is belonging to the parent company, which is vinyl acetate company. So we have interesting polymers like the PVB, the Century Glass interlayer. Okay, coming to why we are here in GPD. So we make different types of interlayers: the standard PVB, the stiff PVB or the structural PVB, and of course the Ionoplast interlayers, which were invented by our previous company, DuPont, around 25 years back. Okay, so we don't just make the PVB, the stiff PVB, and the Ionoplast interlayers. We have some other exciting interlayers which find their application in architectural industry, starting from safety, decorative. You just name the segment, and we can recommend you the solution best matching with your needs. Yeah. And of course, I would like to highlight the Trocifol Extra Stiff Pro, which is the new addition to our portfolio. So it will be referred to as B231. And also, I would like to talk about, so my colleague Christoph, he talked about the sustainability segment, the Trocifol R3, which is based on the concept of reuse, recycled. Yeah, so that's a new addition. And for the automotive, the Sky Vera is another exciting application that we have developed for the automotive segment. Yeah. So coming to the main topic for today's presentation is the improved stiff PVB. So let's see what improvements we have made and what kind of new opportunities and possibilities it can bring for the engineers in this room. So we have a comparison of the Young's modulus of the different polymers that we have, starting with the PVB interlayer at the bottom, represented by the blue line. Okay, and you can see the effect of temperature, its modulus drops. And then we have the gray PVB, the other stiff PVB represented by the gray line. Yeah. And the red line shows the improved stiff PVB, the B231. So you can see we have definitely an edge over the other PVB. And then on the top, we have the Ionoplast interlayers, represented by the yellow line. So you can see, like, even after more than 25 years of its development, it's still the big daddy of all the structural interlayers available in the market. Yeah. So this is for 10 minutes load duration. And then let's look at the 1 minute load duration. For this particular load duration as well, we can see uh, the the improved stiff PB has an edge over the existing stiff PB. Then, okay, now we have got that, this improved stiff PB has definitely an higher Young's modulus, and what this can do for the engineers. So the first step is to do a finite element simulation in Mapla software. So I analyzed a glass balustrade which is cantilevered, supported at the bottom edge with a linear support. Standard height of 1.1 meters, subjected to a line load of 1.5 kN per running meter, and the design temperature was 30 degrees centigrade. Analyzed for two different load durations, 10 minutes, because some standard says the amount of duration of the live load that varies from different country standards. So I analyzed this for two load durations, 10 minutes and 1 minute. Construction was 17.52. And the interlayers was B231 and the other stiff PVB. Okay, so what are the results? So here you can see the blue row is representing the modulus value, which is 7.1 MPa versus the 4.5 MPa for the existing PVB, stiff PVB. And this resulted in lower deflections and stress values for both 10-minute load duration and the 1-minute load duration. So this is definitely bringing down the possibilities of using a thinner glass maybe, or subjecting the same kind of glass construction for probably relatively higher load durations. And also, there is an interest for structural engineers to look at the post-breakage performance of the laminates. So my colleague Ingo Stelger, he was involved into this post-breakage testing on glass beams made with tempered glass. So these are fully tempered glasses, and we intentionally broke the glass, and these were subjected to a point load. This is the 4-point bend test arrangement, which has been placed in a temperature-controlled environment. So the temperature was 23 degrees centigrade. It's a room temperature conditions. Yeah. So after the application of the load, you can see, so the load is not increasing, but the creep is coming into picture. So the deflections at the center of the beam, they are increasing. On the top, we have the B231 laminate, which is the improved stiff PVB. And at the bottom, we have the other stiff PVB. And you can see there is a big amount of difference in the creep behavior. Yeah. So the other way is to plot the curve between the deflections and the time. So here you can see there's a drastic difference in terms of the creep behavior of the existing PVB and the improved stiff PVB. Yeah. Then, so we wanted to test the structural performance and the creep behavior in a real application, which could be a glass balustrade. So here we conducted the balustrade test on in the photograph. You can see there is a glass balustrade which is supported only at the bottom edge, and it is being subjected to a line load at the top. Again, the same construction that we analyzed in Mapla. It is 17.52 FT laminated, 1.1 is the standard height of the balustrade, and subjected to 1.5 kN per meter load. And here we have a comparison of the deflections. So the difference is quite visible because of the lower deflections. It is very much evident that it has got a better structural performance. Yeah, because lower deflections are definitely better. And then we did another test, which is not as per any of the standards. But what we did is we wanted to see that, if they have a glass balustrade with both the glass layers have been broken, and what is the amount of load that is required to cause the complete collapse of the panel. So I have a video to play here. Yeah. So we intentionally broke the glass, and after the brokage, we apply a load onto the top edge of the glass, and to see that what's the maximum load it can sustain before its complete collapse. So this test was done at one of the test labs in Hyderabad, in India. It was hard to find, a lab where you can find a temperature control environment. So the lab had to create a special setup for us so that there is no variation of the temperatures, because the variation of temperatures, a little bit variation of temperatures, can actually cause a lot of difference in the structural performance. Okay. Then we were talking about the glass balustrades. So quite often these applications have their edges exposed to the environment, which means the edge stability is very important to be checked. So we tested the improved stiff PVB with the existing stiff PVB, and we found that it has definitely got a much better edge stability, because here you can see there is a cloudiness that was observed at the corner of the glass laminate after just 3,000 hours only. And whereas the improved stiff PVB, it showed no cloudiness at the edge even after 5,000 hours of exposure to the salty environment in the test. Yeah. Another aspect of open edge applications is that when the glass edges are in a close range of the human eye, the edges should be appealing to the eye. So we found there is a room for improvement in terms of the appearance of the laminate here. So if you look at the laminate at the bottom, this is definitely more appealing to the eyes, to the eyes of an architect especially, because it is blending more with the appearance of the glass compared to the laminate at the top. Yeah. So if you have an application with the glass, where the glass is extra clear maybe, I think this is going to be a more apt choice for the architects. Yeah. Then I'm just moving to the end of my presentation, and would just like to summarize what we have learned in the presentation. Yeah. So the improved stiff PVB has definitely higher Young's modulus, and the higher Young's modulus gets translated into improved structural benefits for the structural engineer. So you definitely have got a better structural performance and better post-breakage performance, as we saw in the videos. Also, edge stability and better appearance of the laminate is an additional benefit that you get from the improved PVB. And also, if you go back to the very first topic about the first chart that we saw about the Young's modulus of the different interlayers. So even after 25 years of invention of the Ionoplast interlayers, they still are the best in the industry when we talk about the structural performance, because we see a big gap in terms of performance of the other structural interlayers versus the Ionoplast interlayers. Yeah. That's all from my side. If you have any questions, comments, I would be happy to answer.